Hey, my name is Jan Ketil Rød, and in this video I'm going to talk about overlays in GIS. Most of the content is taken from the Norwegian textbook GIS Tools to Understand the World. And this is the third video about basic vector operation. Map overlay. In many textbooks you will be referred to Ian Mc Harg. He pioneered what is called the Polygon overlay. And Polygon overlay is one of three commonly divisions of overlay. In many GIS textbooks there is a division between point in polygon, line in polygon and polygon overlay, referring to the three geometric types you have for vector data. What Ian Mc Harg did was to superimpose manually transparent layers on different factors which were important for a decision where to locate the best route for a new highway. Ian Mc Harg was a landscape architect, and he is particularly famous for his book from 1969, Design with Nature. And in this book he is extremely critical to highway commissioners and engineers. Ian Mc Harg meant that these were really destroying beautiful rivers and valleys by designing a highway without any concern about the environment they were put in. Ian Mc Harg's point of departure was that there is always conflicting objectives regarding the land use. And then to be able to do the best planning of a new highway, all these different conflicting objects must be included in the analysis. Only then can you find the best route for a new highway, because that would be then the one that provides the maximum social benefits at the least social cost. So one needs then to have layers of what promote the social benefit and also layers that are displaying then social cost. Let's take some example. When you are designing a highway, of course, three important factors is the slope of the terrain, because that's put an increasing cost the more steeper the terrain is. So what Ian Mc Harg did was then to divide that into groups. So for instance, zone 1, where when you had slope higher than 10 degrees, illustrated by the dark color here, and zone 2, when it was intermediate, and the white one, where the slope were almost flat. Then bedrock foundation is also a factor important for the cost of a new design. And if you have crystalline rocks, the white one, that was then the lowest cost, whereas the other bedrock foundation produced a higher cost because it was more preparation that was needed to do for a highway. Then also the social benefits of an area, if there is a recreation value in the area, was also important to consider. If there is a zone of public open space, of course these are important recreation values which should be protected. So the dark blue ones here, non-urban areas but having a high potential for being recreation, the lighter blue one could also be protected, whereas the white one here, having low recreation potential, maybe okay, better for a highway to cross these areas. And using a light board, these transparent layers were then put together, putting in the slope layer, combining this with bedrock foundation and the recreation values. Now the light or the white areas here, the tracé of the highway is best in these areas. Because here we have then, based on these three criteria, the optimal solution. So what Ian Mc Harg did was to collect value maps or criteria maps for everything which were important for good decision on where the best route for a new highway should go. Having an agricultural value layer and an aquifer value layer and an ecological value layer, and combining these visually by displaying them superimposed on a light board. The dark area are area where you have many interests, both agricultural, aquifer and ecological, and thus this area is bad for development. You should avoid develop in this area. So it's like a visual integration of the layers. And this is also what overlay in the GIS do. It is an integration of two or more layers. It's not just putting the one on top of each other. So often just this having a list of layers in the content menu or the layer list in your GIS is sometimes also called an overlay. But that is not any integrations of the layer. So there are three classical overlays: point in polygon, line in polygon, polygon in polygon, and these are highlighted here, which are often the ones being used as examples in textbook. But all these three geometries can be varied in different ways. You can combine points with points, points with lines, and lines with lines as well. And this becomes quite evidently if you are using the overlay tool available from the Grass tools, which you can also run in QGIS. Here you indicate also the geometry for the input, both the inputs layer. And in this example, two polygon layers are compared. So this is an example of a polygon in polygon. What also comes evident from the Grass tool overlay is that the logical operator is, just as it was central to queries, they're also central to overlay methodology. So two examples of logical operators is the AND operator and the OR operator. And you may remember that the AND operator was restrictive, only providing the common area of the two inputs as the resulting output, whereas the OR operator was much more inclusive, involving everything from the A set to the B set. Everything is then part of the result. So if we illustrate this using map layers, we have two sets here, which are two layers which are combined in an intersect overlay, and then only the common area of the two are resulting, doing an intersect. So just as the AND operator is illustrating. Whereas in the union, you get a cut of the first input layer where this crosses the second input layer, but otherwise you keep everything which is originally part of set A and originally part of set B when you are using the union operator or the OR operator. So these are four kinds of map overlay. There are more of them, but these are four examples and they're logical operators. And this is how they are called in QGIS. There is a tool called the difference. This is corresponding to a not B operator. In other GIS like ArcGIS, it's called arrays. And then we have the intersection, which is A and B, a restrictive operator where only the common part is remained. And we have the union, which is the OR, and the symmetrical difference, which is the exclusive OR. I'll provide some more details on each of these. So the difference tool, it's like the not operator. So we are keeping the first set except the parts which are overlapping the second set, illustrated by the B here. So everything which is B here, we should exclude because we should not have B. So this is just cut away. This works very much like you have an overlay layer, which are used then to exactly do the difference. So it's also like a minus. You take the first input layer minus the second overlay layer, and the result is then the difference between the two. Intersection, again, only keeps the area which is common for the input and the overlay layers, and integrates then the attribute tables for the two. Important to remember, and I'll show an example of that later, the shape is only the one which is common of the two layers, but there is also an integration of their attribute tables. The union, or the OR operator, illustrated here with an input layer and an overlay layer. And notice that there are generated new polygon because the overlay layer is integrated in the input layer. So you are creating new polygons. So whereas there are two polygons in the input and one in the overlay, the output has 1, 2, 3, 4, 5 polygons. And also the attribute tables is updated. So there is an attribute table for the input here, typically with 2 rows and 1 row for the overlay layer. But the output will have 5 rows in the attribute table. And with some no data values, where you only have one of the inputs, like the 2 polygons here, or the one down here where you only have the overlay layer. Because you don't have any attributes from the input layer for this area, and you do not have any attributes from the overlay layer from these 2 polygons. So there will be some no data when you have the union operator. Then the symmetrical difference, or the exclusive OR, the one or the other, but not both. Here we then are excluding the area which 2 sets have in common. So you can have an input layer and an overlay layer, and the part which these 2 layers have in common are excluded from the results. So the first of this, the not operator, the R not B, is then the difference tool in QGIS. And this is one example of how you could want to use the difference. We have a dataset on protected areas, which is the filled light green colored areas here. And you have the proposed protected area, which are the hatched polygons here. But in 2 places, these are overlapping each other. So if you, for instance, want to calculate for each municipality, what are the area of protected land, and what are the area of proposed protected land, and what are the area of the combined protected and proposed protected land. To do this correctly, to avoid that this area here is counted both for the protected and the proposed protected, it should be excluded from the proposed protected. Probably the proposed protected dataset is not updated because this has no status as protected and not only proposed protected anymore. So then you can run a difference and you sort of exclude those areas from the proposed protected, which are already protected. A common problem with overlay, which you may also experience using the difference tool, is that the result are having these small meaningless polygons. This actually looks like linear features, but they are very thin polygons called slivers. And for many reasons, this may be unwanted to keep them. In the grass overlay, there is something you can set as a snapping threshold, so you avoid these to appear. Within the QGIS difference tool, however, I did not find any tool which similarly can resolve the problem of slivers. But in many GIS, there are ways of dealing with these slivers, and also in QGIS, although you don't have this snapping threshold parameter where you can set a tolerance for how near this linear feature can be before they are snapped together, and then avoiding slivers. There are other ways to deal with these, but this will not be covered in this video. I have 3 examples on how 2 layers are integrated when we perform an overlay on them. First example is on point in Polygon, and I use here one input layer, which is points, and showing then the position. It could be GPS tracking of animals. So we have an elk in 1 and 2, and a deer in position 3. And we also have then an overlay layer of polygons with land use categories. So in Polygon 1 we have forest, in Polygon 2 we have pasture, and in 3 we have cropland, and 4 we have developed land. Here we have a point layer as input, which has the same geographical extent as the overlay layer. And then union and intersection would provide the same result. It is only when the geographical extent differs from the two input layer when union and intersection provides different output. When the geographical extent is the same, the tool operates similarly. One principle is that whenever you combine points with polygon using union or intersection, it is the inputs having the lowest geometry, and this is points having 0 dimension because it's have no length and no area, which is then the output. So the result here is a point layer having then the same GPS trackings, but then also the information on what is the land use which this species were occupying. So there are no result from the developed land, the 4th polygon here, because there were no animal inside the area of polygon 4. But there are land use categories then attached to point 1, 2, 3 as a new attribute or a new column in the attribute table. So we are integrating then here the information in 2 attribute tables. So the points are sort of taking with it the area information it crosses. A similar thing happens when we have lines to polygons, and again the 2 input layers here have the same geographical extension, so a union and an intersection would provide again the same result. Here we have a river of length 300, typically 300 meters if it is a projected coordinate system, and here we have also an integration of the geometry, because whenever a line crosses this polygon using union and intersection, new nodes are created. So this one line are cut into 3 lines because it crosses then the polygon boundaries 2 places. The polygon here are properties. So we have properties of land owned by 4 different persons. Hansen, Knudsen, Olsen and Ovesen owns each one of these polygon areas. And the result is then 3 line segments. So of course then the output attribute tables has 3 rows, just as we have 1 row for 1 objects in the input. When we have 3 objects in the resulting layer, we have 3 rows in the attribute table. We have the status still for the attribute we have from the input layer. All of these river segments are protected, but they have different owners because they are crossing 3 different polygons of 3 different properties. Olsen owns this part here, and he has or she has no river crossing his or her properties. So of course there are no row representing Olsen in this output here. One tricky thing is the length here. If you are using shapefiles in QGIS or other software, you would probably have 300 in all of these rows here. Although, of course, the segments are shorter than 300 when it is cut up in 3 parts, it does not automatically update the length. You need to update this length field so the values are correct after a union or intersection. If you are, however, using feature classes in geodatabases in Esri software such as ArcGIS Pro, this updates automatically. So the last example is an example on polygon overlay. We have an input layer with polygon showing the land use as they were for an area in 1963. And the second layer, the overlay layer, also having polygon, is the same area and the land use, which is there 30 years later in 1993. And then one can do here an overlay to see how land use has been changing during this 30-year period. As before, the geographical extent of the two input layers are similar, so whether you use a union or an intersection would then give the same result. We have here what is green, forest, and what is yellow, pasture areas. So these 1 and 3 in 1963 was forest, whereas area 2 were pasture. And in 1993 this has changed. The forest has grown some places and the pasture has grown some other places. And doing a union or intersection, then both the geometry and the attribute tables are combined, they are integrated. Although we have 3 units, 3 polygons, both in the input and the output, there will be as many as 7 polygons in the output. And normally there is 1 row for each object, so when it is 7 polygons in the result, there are 7 rows in the attribute table. And new numbers are generated, and these numbers have no reference to the old one. And you have the attribute from the input layer, which land use type it had in 1963, and you have the attribute for the overlay layer, the land use categories the area had in 1993. And you have here then an updated area measure, but similarly as length for shapefile, this does not update automatically. So this has to be done separately. Now this output may have huge potential for further analysis on land use changes, because for instance, if you are interested in knowing where are the areas which previously were pasture area but is experiencing regrowth, so the forest takes over, so this can then be identified by, for instance, doing an SQL selection of finding all those which have land use type pasture in 1963 and which has got the land use category forest in 1993. So by identifying these 2 areas here, the 6 and the 7, these are those areas which has that interesting land use change. So this was often used exam question I used to pose, how to identify records that in 1963 were pasture, but which is in 1993 overgrown by forest. And this is then an SQL who would provide this answer. So type 63, so this column here should be pasture. So there are also this one here, which would fulfill the first requirement. But since we are using an AND operator, and thus restricting the selection, because we also want this type 93, so the second column here, to be forest. And for this one here, it is still forest also in 1993, so this will not be part of the selection. Here we have not have any land use change. To identify these areas that were pasture but became forest, this is then the result. And it would also be highlighted in the map, these 2 areas. That was all about polygon overlay, and that was all about vector overlay.